Right, let's do another problem. So this one is number 39, combination sum. Given an array of distinct integers, candidates, and an target integer target, return a list of all unique combinations of candidates with the chosen numbers summed to target. You may return the combinations in any order. And the same number can be chosen an unlimited number of times, and so on and so forth. This is a problem that I've done before. I recall searching up the LeetCode solution for this a long ago, and at least it feels like that now. What I can recollect is that, let's say for example, we'll take this first one, 2, 3, 6, 7, for example, right? Essentially what this comes down to what this breaks down to is that for each candidate number, we have a choice. Take the number or leave the combination as is. So at 2, we get 2, or we could leave it empty. At 3, we have 3 choices based on the previous choices. So we can take the 2 again. We could take the 3 with the 2. We could take the 3 on its own, or we could take nothing. At the 6, we have a very similar thing. So 2, 2, and 2. Then 2, 2, and 3. Then 2, 3, and 3. Then 2, 3, and 6. Of course, in this case, we don't want to go back. We don't want to take 2, 3, and then we go back with this combination. So once these are here, we only look at what comes after it. We never look at what comes before. Right? And then we also have 2, 2, 6, 2, 6 on its own, 6, and I think empty. Something like that, right? So this provides a sort of exponential blowup. And will result in an order of 2 to the n runtime, very likely. Something that we could try to do is that rather than holding all of these combinations, use a data structure to keep track of compatible sets and combine them when necessary. So this is a sort of like a DP-like approach, where basically for all numbers from 1 to the target, find the combinations that add up to the number. If a complementary set exists, basically like let's say 0 and target, or 1 target minus 1 example, produce the power set of those two. And maybe it'll make a little bit more sense when I actually dive into example. So let's actually run into an example with this existing one. So for we can start at 0, which will be empty. 1 will also be empty. 2, well, we can say all sets, or yeah, we could make a power set of anything within 1 and itself, as well as if 2 exists. And as a result, our set that is or our list of sets in 2 will just be an array of 2. For 3, something very similar. So power set combo of 1 and 2. But since 1 is empty, nothing happens there. And 3 if it exists, which will just result in 3. 4, we see that there will be a power set of anything, or power set combos of 1 and 3, as well as 2 and 2. And that results in a power set of 2 with itself. 1 and 3 is, again, 1 is empty, so we don't care there. But 2 and 2, well, 2 is occupied, and we, of course, can take an unlimited number of items with itself. So we produce the power set of 2 with itself, which is just 2, 2. Similar story for 5. So 5, we can take 4 and 1. So we can do 4 and 1, 2, 2 and 3. So that produces 2 and 3, so that produces just 2 and 3. There's nothing with 4 in it, so we can safely ignore that. 6, similar thing, 5 and 1, 2 and 4, 3 and 3, and 6, if it exists. Well, 5 and 1, there's no 1. 2 and 4, we can get 2, 2 and 2. 3 and 3, we can get 3, 3. And of course, we can get 6. For 7, we can get 6 and 1, 5 and 2, 4 and 3, and 7, if it exists. So 6 and 1, obviously nothing. 5 and 2, we get 2, 3, and 2. 4 and 3, we get 3, 2, and 2, which may pose to actually be a problem then. Because those sets are not unique. And then 7 obviously exists, but because this 4 and 3, because this 4 is composed of this 5 is already composed of 2 and 3. This 4 is also composed of those 2 and 3. Let me think about how to eliminate those duplicates. If we check only the most recent set, will that help? But would that get rid of any combinations that we would want? So 2 and 4, 3 and 3. We shouldn't just check the first combination that actually exists, because we'd miss out on this. Unless we want to talk about like, oh, as long as it's the first set that we haven't seen, or it's the first set that is non-empty, and they are not the same, it's not the same like set. So this would be 7 and 1, 6 and 2, 5 and 3, 4 and 4. So 4 and 4, that produces that. Let's see, 7 and 1 doesn't exist. 6 and 2. 6 and 2 produces 2, 2, 2, and 2. Ooh, that's a duplicate as well. 332 is fine. 62 is fine. Interesting. How can we get rid of duplicates? Again, more thinking needs to be done off camera. Otherwise, these videos are gonna take like hours. Man, both of these problems today have been incredibly rough, but I think I'm at the point with this problem where I'm fine with where it is. So, I decided to take a peek at the related topics thing at the bottom of this LeetCode problem. And the thing that it told me is that this is potentially a problem that could be solved with backtracking. I have not been sort of brushed up on backtracking, so I went back to one of my favorite videos on this, which is this one by Back Software Engineering. This is a really good video on backtracking and sort of breaks it down into really sort of understandable and memorizable components, being a choice, sort of what is the choice that we're making at each sort of iteration, a constraint, sort of what do we want in order to continue to recurse on our choices, and then what they describe as a goal, but I'm going to say converge, basically the base case or the goal, the ending condition for us. In this case, our choice is on a set. For each value within our set, we want to basically choose, or within our candidates array, we want to choose whether or not we want to take the element or not. And that choice is essentially contingent on two constraints. One, the candidate must, along with the rest of the list that we have already, it must not exceed our target. If it exceeds our target, then we're done. Right? We don't need to go any further because we've already blown past our target. We don't need to recurse on that part. Similarly, we don't want to go back and grab older candidates that we've already explored. And the reason why we don't want to go back and we only want to look at our current candidate as well as beyond is that if we look backwards, we run into the risk of basically exploring options that we've already explored before. We've already looked at these sets and we run into duplicates. Our goal condition, or our convergence, is when our total existing amount along with our candidate adds up to exactly the target. In that case, we will add it into our solution set, and then we will add it to our solution set and we will return that solution set. If we find a solution set within one of our recursions which is not empty, so there was a solution that we found within that sort of recursion, then we will add it into our set. I'm going to comment out these prints and then throw in another submit. You can see that I've already tested this out before, but it seems like the prints do influence the runtime by a decent amount. So yeah, this is basically my introduction, a very rough introduction to backtracking. And honestly, the road to finding this solution, once I sort of like thought about it within the terms, within the framing of a backtracking problem, wasn't actually necessarily too difficult. It took me about, I would say, around 10 minutes to actually code out the solution, but it took me a lot more time to sort of think about it and break it down into this backtracking solution. I think one really, really important part that they bring up is towards the end here, and that is talking about when a solution like backtracking is likely, and that is when you hear the terms generate all or compute all solutions. And that is where something like backtracking will probably be used, as well as the runtime being some flavor of exponential. But in any case, I would consider this another sort of solution peaking problem. Really rough considering that we've had 2 of these now today for both of my times, which really sucks, but hopefully we get better at these problems as we go on. But in any case, I hope you learned something, and I'll see you for the next problem.